thank you all for this opportunity to talk about my research. My name is Faustin Gashakamba, and I did this research as my thesis for the program of Master in Geoinformation Science at the very innovatively called University of Rwanda. In terms of background, we know that land degradation and soil pollution are some of the most pressing issues in terms of environmental protection and development in general. So soil erosion is one of the contributing factors to these two factors. In terms of water pollution, soil erosion contributes to siltation of water courses. But also in terms of land degradation, soil erosion is one of the factors of degrading fertility. And fertility in our agricultural societies, fertility is a big issue. So I wanted to look at this issue of soil erosion in a small watershed called Yanze. Because this Yanze watershed is located near Kigali city, and it's the main source of water supply for this city, but also is very inhabited, is densely inhabited as any watershed near a big city would be. But there has been some initiatives before from different players, government projects, NGO players doing soil conservation projects in that watershed, and the results have been mixed. I mean, some projects were successful depending on their objectives, some others weren't. And mostly the problem is almost always lies with the budget, because these soil conservation projects, they are very expensive. I'm saying Yanze is a small watershed, but still is a big area, so you need a lot of money. And sometimes it's all of the time that money is not there. So that's why you need some kind of prioritization. Whenever there is a soil conservation project, you cannot apply the same measures everywhere. You need to prioritize some areas within your study, your area of interest. So I was looking and see, is there a way hypsometric analysis can help in terms of prioritization of soil conservation measures in a given area? So that's what my project set out to see, to know if we can use hypsometric analysis, some hypsometric metrics, to use them as a predictor of erosion in an area. But also some other objectives of the project was to look at how we can use GIS to conduct a morphometric analysis of watershed, and also develop a risk profile, an updated risk profile for this Yanze watershed. We have erosion soil loss studies that have been conducted nationwide or a bigger region and a bigger scale. And the resolution of the studies were not fine enough to be used at local level. So one of the objectives of the project was also to establish a soil risk profile for this watershed. The methodology, the study had three components, if I can say. These are normally, for those who are familiar with the revised universal soil erosion equation, there are some factors. Normally there are 6, but 2 are combined here, so we have 5. So the first one is called rainfall erosivity. Rainfall erosivity normally is calculated from rain intensity and energy data. It's called the hydrograph data. It's very detailed rain event data to say every minute the intensity of the rain was this, it evolved like this. You have this for every rainfall event for the whole year. So this kind of data doesn't exist anywhere in Africa, I could say. So for me, I used normally available data, daily rainfall data, and there are some empirical equations that were derived to calculate rainfall erosivity using such data. For this cover management factor, this is a way to express the role of vegetation in controlling rainfall intensity to cause erosion in area. An area which is covered, heavily covered by vegetation, that vegetation will reduce the intensity of the raindrops to the soil. It also increases infiltration. So where there is a lot of vegetation or the land cover is like forest or some more highly vegetated land cover type, then the cover management factor will be low. If there is any vegetation at all, then the cover management factor will be high. This one called support practice factor, this is to express in the Russell equation, to express the kind of existing soil conservation measures. If the area is terraced, if there is mulching, what kind of agricultural system used. This one is captured here in the support practice factor. For this, we also had to use land cover maps, and there are some other factors which enters into this equation and to calculate this one. The land cover map was developed using Sentinel data imagery. So soil erodibility, this is to capture the susceptibility of soil to erosion. Normally, this is calculated from texture, soil texture data, what fraction of silt, what fraction of clay, what fraction of organic matter, sand, and so on. For this, we use soil attribute map, but we couldn't find local data, so we used data from Africa Soil Information Science. It's a global database established by ISRIC. And this slope length steepness factor or topography factor, it's used to capture the ruggedness of the terrain. So for this, we used a DM that's available, a 10-meter DM that's available in Rwanda. So this is the first component of the study to establish the soil profile, the soil erosion profile of the landscape. The second component was about hypsometric analysis of the area. Here we need them, of course, and then hydrologic network that the data was available at the office in charge of water in Rwanda, and then we delineated the area into sub-watersheds. In total, we delineated 93 sub-watersheds, and for each sub-watershed, we calculated an hypsometric curve and also an hypsometric integral using different software, including R. Then the two maps, this one, the soil erosion risk map, and the hypsometric map were correlated to see if there is some correlation. So we conducted that correlation analysis, and that was the end of the study. That was methodology. Now, some of the results. The first component about the hypsometric analysis of the watershed. So this is the watershed. The area in dark green, the area where the hypsometric integral is high. The area in yellow, light green is where the hypsometric integral is low. So in general, for the whole 93 watersheds, the lowest we could find, the lowest hypsometric integral was 0.5, the highest was 0.9. As you can see, all of the sub-watersheds were at equilibrium stage, but mostly were at Yanze stage. Normally, equilibrium stage is between 0.4, 0.6. Beyond 0.6, it's the landscape is said to be at Yanze stage. Only below 0.4, that's where you can say the landscape is mature. So no sub-watersheds were found to be at a mature stage. That's what I can say. In terms of spatial distribution, general pattern you can see is that the downstream of the watershed is more it is more at a mature stage compared to the upstream stage. In terms of statistical distribution, here I put the lines to show which sub-watersheds are in the mature stage, in the equilibrium stage, in the Yanze stage. As you can see, most of the sub-watersheds are in the Yanze stage. Only a few are in the equilibrium stage. No sub-watershed was found to be in the mature stage. This the mean of the hypsometric integrals. So you can see the mean is well in this Yanze stage. What does it mean? It means that all the sub-watershed in the study area are still undergoing intense erosion. And when I'm saying undergoing erosion, this is a geological scale. It's not to say that last year it was the erosion was this way. This is at geological scale, time scales, and as we will see later on, the correlation with the actual erosion happening there is still small. In terms of soil erosion estimation, as I mentioned, there are 5 factors that were calculated. This is the rainfall, this is the soil, this is the topographic factor, this is the land cover factor, and this is the support practice factor. These are the maps. It's not necessary to go into numbers, but as you can see, for instance, for the topographic factor, you can see always here in these maps, the high means bad. It's higher erosion. Low, it's better. It's low. Like the overall equation is to multiply all of these. So if you multiply all these and there is somewhere some of these have low values, so the soil loss will be low. So when we have red, it's bad. It means there is a susceptibility of high erosion. When it's green, it's better. The final result, this is the final map. This one. So it shows the soil erosion after multiplying all these factors, and the total was found to be 12 ton per hectare per year. And I had to discretize, if I can say, to make this soil erosion risk factor so that I can make the correlation. The aggregation method I used, the statistic I used is mean. It would have been better to use the median, but since this is a continuous raster, it was difficult. I have some ideas from my supervisor, but for the time being, we use the mean statistic to create this soil risk profile. For each sub-watershed, we calculated the mean soil loss in that sub-watershed. And that's what we put here. And now for the correlation between hypsometric integral and soil erosion risk, we conducted a linear regression, and we found that some 7%, the R squared is 0.07, so it means that 7.7%, that almost 8% of the variation in the variation in the erosion was explained by hypsometry. So you can say this is small, it's a small correlation, but if you are trying to prioritize erosion, if you can already be sure that this area has 7% higher chance of erosion than the other, you can have a starting point of prioritizing your areas. But also, what's interesting is that the p-value was small, which means that this 7.7% relationship was genuine. It's not due by chance, if I can say. So you are confident that this relationship we are looking at is genuine. So this is almost already good, but in my recommendations, I'm suggesting that we include many other morphologic metrics in the correlation analysis. So we make a multivariate analysis, so that maybe if you reach 30% of the variation, it will be already good for prioritization, so that you can say, I can use morphometric analysis as a prioritization scheme for soil erosion in an area. Some challenges I met during this study. There are some data sets, for instance, like I said, on soil texture data. I wanted soil texture data. Locally, this kind of data set is not available. I was told the project, which there is a national project ongoing right now, which will have such data, but this will be like next year. So I had to use data from international databases, which not always good, because sometimes this data set requires the resolution for this one, for instance, was 250 meters, while I was looking at the scale of 10 meters resolution. So I had to resample this one. So it was one of the challenge. Another one was the accessibility of data. The data I was able to get access to is the Sentinel data, the freely available. That's 10-meter resolution. But for mapping, for instance, run practices, like you want to see where the terraces are, because these ones I had to do manually. You want to see where there is a banana plantations, or where there is some kind of agriculture practice that requires matching and so on. So this one I needed very high resolution map data. The data is already available in Rwanda. There's a mission, WorldView mission, that covers the whole Rwanda. The images are there in the National Statistics Office, but the administrative procedures to reach that data were too long compared to the timeline I had. So I have to make do with what I had. I used Sentinel-2. Another challenge was COVID. That's general, but it only affected my timeline. Otherwise, it didn't affect the quality of my work. So thank you. That what I had to say. If there are some more needed clarification or questions or contribution inputs, comments, all these are welcome. Thank you, Chair.
Thank you, Faustin, for your presentation. One simple question that I have. From your analysis, which areas should be prioritized?
Normally, if you look at here, this is the map. It shows the area which are undergoing much erosion. These ones in red, they want to be prioritized. But this map was calculated, was established using Russell. So that's what I wanted to avoid. We wanted to see if we can arrive at such a map without using Russell, by using hypsometric analysis.
Yeah. Do we have? Yes, we have some questions in the audience.
Smaller than that, 0.03. So it's smaller than that. So that's why I say this relationship was not due by chance. That's what you. Okay.
Yes, I'm asking at the significance of that p-value. Of course, I see your R squared there is 0.07. That is the coefficient of determination, which is quite low. Yeah, it should be approaching 1.
Yeah, I get you. And I mentioned that this is a small explanatory. So the explanatory power of hypsometry vis-a-vis erosion in landscape, at least in my study area, was small. So hypsometry was explaining only 77% of the variation. So it's small. But I was suggesting that in future studies, if you would maybe add morphometric indices, you can at least reach 50%, if I can say. So if you reach 50%, you are in an area you want to prioritize, you want to make a quick analysis of area to know which area to prioritize without going into deep soil loss studies. Then if you have a quick way to get, because morphometric analysis is something you do on desk, doesn't require you to go on field, provided that you have detailed digital elevation models, and these ones are available nowadays very cheaply. So I was saying, if you can reach 50%, that will be good. Here we are still at 7% using only one morphometric analysis. Here I only used hypsometric integral. So if you use others, there are many morphometric indices. Maybe I was hoping we can increase that. But at least what I was saying, at least we know that this is genuine. This relationship we are looking is genuine. It's not, we didn't reach that by chance. Thank you. Doctor,
Thanks. Mine is just a very quick one. One, I was just curious about the source of the DEM. And two, in light of the work you have done, what would be your management interventions you would recommend? What, if your boss asks you, you have been on this master's for 1 or 2 years, what would you recommend from a management perspective? Thank you.
Okay, thank you, Dr. Anthony. The source of the DM, we have in Rwanda a DM that was developed by former Rwanda National Resources Authority, to be called RNRA. Now it has been disbanded, but the data set is still available, not in publicly shared like we're looking at the spatial data infrastructure. In Rwanda, we don't have yet such a facility, but at least that data set is available. But we also have another one with good metadata, and so but that one is 30 meters resolution. So I used the one with 10 meter resolution. Regarding recommendations, like I said, we are still low in terms of saying we can use hypsometric analysis as a predictor of soil erosion because the relationship is still low. So I was recommending to continue the studies to increase this relationship by including other morphometric indices. There is a few I have suggested. So I hope anyone will come after me and conduct this analysis, or myself in the future, I could continue with this kind of work.